Welcome students to session 5, and this is video 9, chapter 1, real numbers. Well, only two concepts are left and then we are done with the chapter. I'll do one of the concepts today, correct? Please observe and understand. 2, 3, 5, 7, 11, 13, 17, 19, 23 and so on. What are these? Prime numbers? Correct. They are all prime numbers. 4, 6, 8, 9, 10, 12, 14, 15, 16, 18, 20, 21, 22, 24, 25, 26, 27, 30 and so on. These are all composite numbers, correct? These are all primes and these are all composites, correct? Children, the next concept of ours is square root of 2, square root of 3, square root of 5, square root of 7, square root of 11, square root of 13, square root of 13, 17, square root of 19, square root of 23. Means square root of any prime number. Square root of any prime number P. P for prime number. It may be 2, 3, 5, 7, 11, 13. Any prime number is irrational number. Is irrational number. You can consider this as a theorem as well. This is what we are going to prove. Root 2 is irrational. Root 3 is irrational. Root 5 is irrational. Root 7 is irrational. And from the point of view of board examination, this question is very important. A 2 marks question can be asked. Show that root 13 is irrational. Prove that root 7 is irrational. Correct? Fine. Well, what about this composite numbers? Let's take their square roots. Square root of 4, square root of 6, square root of 8, square root of 9, square root of 10, square root of 12, square root of 15, 16, all square roots. Let's take their square root. And what do you find, children? All are not irrational. What is square root of 4? It's 2. What is square root of 9? It's 3. What is square root of 16? 4. What is square root of 25? 5. So square root of 4. 4 is a composite number. Square root of 4 is not irrational. Square root of 9 is not irrational. Square root of 16 is not irrational. Square root of 25 is not irrational. But all the composite numbers between 4 and 9, they are irrational. Composite numbers between 9 and 16, 10, 12, 14, 16, they are irrational. Composite number between 16 and 25, their square root is irrational. Okay? So one thing is for sure, square root of any prime number is always irrational. Whereas square root of all composite numbers are not irrational. Square root of few composite numbers are rational. Which composite numbers? Which are perfect square, like 4, 9, 16, 25. What would be the next? Correct? Root 36. Next, root 49, root 64, root 81 and so on. Those composite numbers, their square root is always rational. But the remaining ones are irrational. Forget that. My aim is to show root 2 is irrational. Root 3 is irrational. This is our next concept. And from the point of view of examination, as I have already told you, it's very important. Okay? So please pay attention. Children, let me tell you, this is a difficult concept to understand. But few things, few pre-preparations if we do, if we revisit few things that we have learned in 9th standard, okay, then this concept is going to be very easy for you. Alright? So before we prove this, let's pre-prepare ourselves to understand this concept very well. Okay. First, let us see what are rational and irrational. Rational numbers and irrational numbers. I won't go in detail because you have already learned in 9. And if you want to see it again, if you want to revise it well, you can see my video of standard 9. It's not yet prepared. I'm preparing it. Okay. Fine. Rational numbers. There are two types. Terminating decimal and non-terminating but recurring. Non-terminating but recurring. And what are irrational numbers? They are non-terminating. Non-terminating. Alright? But and non-recurring. Non-terminating and non-recurring. Alright? Now what do you mean by terminating decimal rational numbers? Say suppose you have 3 upon 4. Here you have 1 upon 3. And here you have root 2. Square root of 2. Alright? I'll divide this 3 by 4. 0.0. 4 sevens are 28. 2 0. 4 5s are 20. 0. So the division stops. Division stops. Stops means terminates. The other English word for stops means terminates. You must have heard of terminal, railway station terminal, Bandra terminus, CST terminus. Alright? From there, the train doesn't go further. The train stops. That is the last station. So terminates means stops. So this is terminating decimal. This is what? Terminating decimal. Division stops. So further division doesn't continue. So after 2 digit, the answer is done. Here 1 divided by 3. 0.0. 3 3s are 9. 1 0. 3 3s are 9. 1 0. 3 3s are 9. 1 0. Now you got the idea. You will keep on getting 3 3 3 3. Endless. So this is non-terminating. The division doesn't stop. This digit will continue. It doesn't stop. It non-terminates. So this is non-terminating. But what is happening? 3 3 3 repeats. Repeats means reoccur. Reoccur. It occurs again and again. So that is repeating. So you can write in short 0.3. And whatever is repeating, recurring, you can put bar over it. So this is how you can write briefly. So this is non-terminating. Endlessly the division continues. Alright? And the answer is 0.3333333. Endlessly you get 3. So that is non-terminating but recurring. It reoccurs. Now root 2. I won't go into this division. I'll write the answer directly. In 9th standard textbook you have seen that root 2 is 1.414023562375301688724209 dot. When you find the square root of 2, this is the answer 1.41, and endlessly the division continues. You can watch that video once it is prepared. I'll put on YouTube and you can watch from there. Okay? How to find square root of numbers which are not perfect square. Now you see, the division continues. So it's non-terminating. Terminate nahi ho raha hai. So it is non-terminating. And see if anything reoccurs. 4 1. Then it becomes 4 2 1. Then 3 5 6 2 3. See 3 5. Here 3 occurs. But then 3 7. Then we have 3 0. 9 5. 5 6. Here 5 0. 4 1. 4 2. 4 8. So every time it's different. It is not appearing again and again. It doesn't reoccur. Do you understand? So this is non-terminating, non-recurring. Such numbers are called irrational numbers. And that is what we are going to prove. Square root of every prime number is irrational. So I hope this is clear. Okay. This is just pre-preparation, children. Let's see another concept. Okay. When you divide 18 by 2, when you divide 10 by 2, or when you divide 15 by 3, 2 9s are 18 and 0, 2 5s are 10 and 0, 3 5s are 15 and 0. Children, in this case, we have learned this. 2 is called factor. 2 is called factor of 18. 2 is called factor of 10. 2 is called factor of 10. 3 is called factor of 15. So divisor is a factor of dividend. Divisor is factor of dividend. If remainder equal to 0. If remainder is equal to 0. If remainder is 0, then divisor is factor of dividend. Conversely, this 18 is called multiple of 2. This 10 is called multiple of 2. This 15 is called multiple of 3. Alright? So, dividend is called multiple of divisor. But condition, if remainder equal to 0. Got it, children? Remember this concept very well. Here, I can say 2 divides 18 exactly. This is another way of writing factor. 2 is a factor of 18. That means 2 divides 18 exactly. 2 is a factor of 10. That means 2 divides 10 exactly. This is another way of writing. 2 divides 10 exactly. 3 is a factor of 15, which means 3 divides 15 exactly. So 3 divides 15 exactly. Conversely, if 3 divides 15 exactly, then 3 is a factor of 15. If 2 divides 18 exactly, then 2 is a factor of 18. Correct? Are you getting me? Sure. Next. 15 is a multiple of 3. If 3 divides 15 exactly, 15 is a multiple of 3. 18 is a multiple of 2. And 10 is a multiple of 2. Children, how to express multiple, please? Which are the multiples of 2? 2, 4, 6, 8, 10, 12, 14 and so on. That means 2 into 1, 2 into 2, 6 is 2 into 3, 8 is 2 into 4. It's not 2 pointer, it's 2 into children. 2 into 4, 10 is 2 into 5, 12 is 2 into 6 and 14 is 2 into 7 and so on. So 2 is common here. So I can say 2 and for 1, 2, 3 I can put k. So if I write 2k, 2k is multiple of 2. 2k is multiple of 2. Are you getting me? One more example. Let's take multiple of 7. 7, 14, 21, 28, 35 and so on. So you may write 7 into 1, 7 into 2, 7 into 3, 7 into 4 and so on. What is same? 7. So I can write 7 and for 1, 2, 3, 4 I can write k. So 7k is actually representing multiple of 7. Boliye now. 4k, it's multiple of 4. 5k, it's multiple of 5. 3a, it's multiple of 3. 11b, it's multiple of 11. Got it? Understood this? So here 15 divides 3 exactly. So 15 is a multiple of 3. So I can write for 15, I can write 3k because it is multiple of 15. 18 is multiple of 2. So I can say 2k. For 18 I can say 2k. 10 is multiple of 2. So for 10 I may say 2a, which because 2a is a multiple of 2. Are you getting me? So this concept also would be required. If you understand this well, you will understand that thing also very well, children. Please pay attention. Okay. Two more things, children. As a part of our pre-preparation, see, 2 divides 4 exactly. Is it true? Yes. So you can say 2 divides 2 square exactly. For 4 I wrote 2 square. Now even if I remove 2 square, this square if I remove, 2 divides 2 exactly. That is true. This is true. This is also true. And this is also true. 7 divides 98 twos are 180 and 196 exactly. Now we'll check if you want. 196 divided by 7. 7 twos are 14. 5 remains. 7 eights are 56. Correct? So it divides. I'm sorry. Yeah. It divides 196 exactly. I want a perfect square number. So I'll take perfect square number 49. Okay. 7 divides 49 exactly. No doubt about that. So 7 divides 7 square. So obviously 7 will divide 7 even if I remove square. Now look. A divides m square. Then can you say A divides m? Definitely. P divides q square. Can you say P divides q? Yes. Correct. And that is the statement of theorem 13. Sorry, 1.3. Theorem 1.3. Theorem 1.3. For two positive integers a and b, if a divides b square exactly, if a divides b square, there are two positive numbers as I have chosen 7 and 49, I have chosen 2 and 4, any two positive numbers such that a divides b square exactly, then a always divides b. This is the statement of theorem 1.3 which we'll be using quite often in that proof. Okay. Last but not the least, pre-preparation. Any rational number is represented in which form? A upon b, where a and b are co-primes. Means what? HCF of a and b is 1. 2 upon 3. Follow 2 is 1 2s are, 3 is 1 3s are. See, look here. What is the HCF of 2 and 3? HCF of 2 and 3 is 1. When HCF numerator and denominator is 1, we can say 2 and 3 are co-primes. So any rational number when it is represented, there are two conditions now. Say, instead of writing 2 upon 3, I could have written 6 upon 9. But then if you reduce 3 2s are and 3 3s are, so ultimately you are getting the same. So any rational number is always represented in its reduced form. Kabhi bhi hum say children, if you someone asks, how much apple do you want? Your mummy removes one apple from a refrigerator and she asks, how much apple do you want? You will say half. Means make two equal parts and give one. Will you say 10 upon 20 parts? Will you say that? Give me half. This also means half only. 10 ones and 10 twos, it's half only. But you will never say give me 10 out of 20 parts. Make 20 equal parts and give 10. You will say make 2 parts and give 1 part out of that. Is that clear? So whenever any rational number is represented, yes, the GCD of its numerator and denominator is always 1. Which means this numerator and denominator numbers are always co-primes. Is that clear? Fine. Co-primes means what? These two numbers will have no common factor other than 1. 1 के अलावा कोई भी factor common नहीं हो सकता है. Is that clear? Fine. What about 4 upon 6? Are 4 and 6 co-primes? Let's find out the factors. 2 into 2 into 1, I'm writing that, 6. 2 into 3 into 1. So which are the common factors? Common factors 1 and 2. Common factors are 1 and 2. So besides 1, 2 is also common. So you cannot say 4 and 6 are co-primes. One common factor of any two numbers or any three numbers or any infinite numbers. Correct? But if you have more than a common factor other than 2, then it is not co-prime. Are you getting me? Now look here. 2 divides 4 exactly. 2 divides 6 also exactly. That's why 2 is common factor of both. 2 is factor of 4. 2 is factor of 6. So 2 is common factor of 4 and 6. So 4 and 6 cannot be common because it has common factor other than 1. Are you getting me? And under such circumstances you can reduce 2 2s and 2 3s. Now this reduced form has numerator 2 and denominator 3, which are co-primes. Clear to you, children? Fine. Now, very difficult concept. It's theorem 1.4, I think. Theorem 1.4. I don't know whether it is a mistake of textbook. I would say it is a mistake of textbook, but you can never say that because God knows what logic they have applied by putting this statement as theorem 1.4. I feel the statement should have been like this. If P is prime, then show that square root of P is irrational. This should have been the statement, but they have said P is prime nahi. If 2 is prime, there is no doubt about that, then square root of 2 is irrational. This is what we are supposed to prove. Children, how to prove that square root of 2 is irrational? There are two methods. We can start with what is given in the data. What is given? 2 is prime. That's it. Nothing else is given. 2 is prime. You can start with that data, that given statement, and use logical reasoning, and at the end you show that square root of 2 is rational. Or what you have to prove? Root 2 is irrational. Suppose converse of that statement. What do you have to prove? Root 2 is irrational. So how do we start our proof? By supposing a statement that root 2 is irrational. Alright? So this is another method of proving the statement. The first method, pick up the given condition, use logical reasoning and reach this destination. Or pick up the statement which we are supposed to prove, make converse of it, uska ulta kar do, opposite kar do. Suppose that statement, use your logical reasoning and show that what you have supposed is wrong. If that is wrong, then what is correct? Let's see. Children, fine. Solution. It's tough, children, not easy. Suppose root 2 is rational. Suppose root 2 is rational. Clear that? i.e. root 2 is equal to a upon b. यदि ये रूट 2 रेशनल है तो कोई भी रेशनल नंबर a upon b फॉर्म में रिप्रेजेंट कर सकते हैं. If root 2 is rational number, then any rational number can be represented as a upon b form under the condition where b is not equal to 0 and HCF of a and b is equal to 1. Call it result 1. HCF of a and b equal to 1. Or you may say where a and b are co-primes. Where a and b are co-primes, or you may write HCF of a and b equal to 1. Clear? Now what you will do? Please, cross multiplication. So root 2b is equal to a. Correct? Presence of root. I don't want root. So if I want to get rid of root, I am going to square this left hand side. I can't do that in the equation. If I take square on left hand side, I'll have to take square on right hand side. This is Euclid's property. So therefore, square of left hand side is equal to square of right hand side. Left hand side is root 2b and this is a. Therefore, square of root 2 is 2. Square of b square is, the square of b is b square. That is equal to a square. I am going to call this as result 2. This as result 2. Children, now it's going to be difficult. Can you see 2 here? Can you see 2 here? It means 2b square is a multiple of 2. 2b square is multiple of 2. Please, 2b square is a multiple of 2. Do you remember what I explained? 4k, multiple of 4, 5k, multiple. 2 should be there, here anything. So it's a multiple of 2. But now this 2b square is equal to a. So you can say a square is a multiple of 2. A square is multiple of 2. Are you getting me? If a square is multiple of 2, then you can say 2 is factor of a square. 2 is factor of a square. So this 2 divides a square. If it is factor, 2 divides a square exactly. I hope you understood. This is difficult part. The step from here to here is difficult. 2b square is multiple of 2. That means a square is multiple of 2. So that means 2 is factor of a square. That means 2 divides a square exactly. Therefore, 2 divides a. If it divides a square, 2 divides a exactly. This is result 3 by theorem 1.3 if you remember. Okay. Now see what does this say. यहाँ से फिर से twist हो रहा है. 2 divides a exactly. So 2 is a factor of a and a is a multiple of 2. A is a multiple of 2. If a is a multiple of 2, I can write a is equal to 2k. 2k is multiple of 2. I introduce another variable. A is multiple of 2. That means a is equal to 2k. Squaring both sides. A square is equal to 4k square. I have written directly. A square is equal to 4k square. Somewhere we have value of a square. See this result 2. What is a square? 2b square. Substitute that. And why I squared this? You can realize the importance. You can realize that step. Because I want to substitute value of a square. So I made from a square. 2b square is equal to 4k square. Please, 2 1s are 2 2s are. Therefore, b square is equal to 2k square. Again children, 2. So this is multiple of 2. 2k square is multiple of 2. But 2k square is equal to b square. So b square is multiple of 2. B square is multiple of 2. That means 2 is factor of b square. Therefore, 2 divides b square. Therefore, 2 divides b. Result number 4. Children, look. What is result 3? 2 divides a. Result 4. 2 divides b. Again difficult. Try to understand. 2 is a factor of a. 2 is factor of b. That means 2 is a common factor of a and b both. 2 is common factor of a and b both. So the GCF, HCF of a and b cannot be 1. 1 तो common होता ही है. But here result 3 and 4 shows that 2 is a common factor of a and b. That means the HCF of a and b cannot be 1. By 3 and 4, it follows that HCF of a and b cannot be 1. Don't say HCF of a and b is 2. Because you may have further more factors. Alright? Common factors. So it is not equal to 1. You got one extra common factor. So now HCF cannot be 1. Hooray children. HCF is not 1. but HCF is 1. That is hypothesis. This is the truth. ये तो सच्चाई है, इसको हम नहीं बदल सकते. This is the truth. We cannot change that. So what we proved or what we got through logical reasoning is wrong. This is wrong. Why this is wrong? Because it contradicts the hypothesis. जो सच्चाई है उससे कहीं दूर है ये. Are you getting me? So here, which contradicts the hypothesis in one. ये स्टेटमेंट जो है contradicts the hypothesis in one. इसके साथ मेल नहीं बनता है. जो contradiction आया उसका मतलब क्या? Our supposition is wrong. I'll continue here, please. Therefore, our supposition that root 2 is rational is wrong, is not true, is incorrect. Then what is correct? What is true? What is right? अरे भाई, only two possibilities. root 2 rational होगा या root 2 irrational होगा. root 2 rational है, ये गलत है, तो सही क्या है? root 2 irrational. That's it. Only other alternative. Therefore, root 2 is rational. Proved. Did you understand? Did you understand? Yes, children, I am sure you must have understand. But if I give you next statement to prove, you won't be able to write because you need lot of practice. You need lot of practice. So we'll see two more sums here. Okay? Please pay attention. Number 2. That was theorem 1.4, but I believe it should not have been that statement as a theorem. Anyway, number 2. Prove that root 3 is irrational. It is irrational, we have to prove that. Okay? This time I'll write little bit in order, okay, because I've got full board for writing that. Solution. Alright. I start with supposition. Suppose root 2 is rational. Suppose root 2 is rational. I.e. that means root 3 can be written as P upon Q. Instead of A upon B, I wrote P upon Q. My choice. Where Q is not equal to 0 and HCF of P and Q is equal to 1. And this is result 1. ये सच्चाई है कि यहाँ P और Q हमने जो लिया है, they are co-primes. Their HCF is 1. चलिए, cross multiplication gives me root 3. Root 3Q is equal to P. Squaring both sides, 3Q square is equal to P square. So 3 divides P square. 3 divides P square exactly. I'm going to call this P square as result number 2. If 3 divides P square, then 3 divides P, result 3 by theorem 1.3. 3 divides P exactly, then P is a multiple of 3, i.e. P is equal to 3K. P is equal to 3K. Therefore, squaring both sides, P square is equal to 9K square. Correct? Now what is P square from 2? 3Q square. So I am putting that value of P square from here. 3Q square. 3Q square is equal to 9K square. 3 ones are 3 threes are, which gives me Q square is equal to 3K square. Now see on the right hand side, 3K square. That means this is multiple of 3. So Q square is multiple of 3. So 3 divides Q square exactly. Therefore 3 divides Q square. 3 divides Q square. Therefore 3 divides Q. Result number. This is 3 and now it's result 4. आप देख लीजिए 3 divides P. 3 divides Q. Are you getting me? 3 divides P and 3 divides Q. So that means 3 is a common factor of P and Q. So the HCF of P and Q cannot be 1. Abhi 3 to common factor aa gaya. It cannot be 1. So by 3 and 4, it follows that HCF of P and Q cannot be equal to 1. This contradicts the hypothesis in 1. जो 1 में सच्चाई है उससे उल्टा है. ये तो सच्चाई है, वो सच्चाई रहने वाली है, तो मतलब ये गलत है क्योंकि हमने सपोजिशन गलत किया. Therefore our supposition that root 3 is rational is incorrect. This time I put the word incorrect. Now root 3 is rational, that is incorrect. So what is correct? Root 3 is irrational. Therefore root 3 is irrational. Proof. Did you understand? Do you need one more example? Yes, I think so. So let's see. Okay. Yes. Irrational number. Prove करना है. Square root of prime. Can you give me one prime number? Yes. Vraj, I can hear you. What you said? 23. All right. I'm taking 23. 23 is prime and square root of prime is irrational. That is what we are going to prove. Converse. Suppose करेंगे. Suppose square root of 23 is rational. अभी ये rational है. So you can write in the form A upon B, P upon Q, M upon N. This time I'm going to use M upon N. है ना? चलिए. I.e. that means root 23 is equal to M upon N. Where that denominator N cannot be 0 and HCF of M and N is equal to 1. And that is the result 1. Same way we'll continue. We have to get rid of square root. This is 23. Therefore, follow. Root 23 into N is equal to M. Squaring both sides. 23 N square is equal to M square. 23 को देखो. So ये multiple of 23. So M square is multiple of 23. So 23 is factor of M square. Therefore 23 divides M square. इसको result 2 कहेंगे जिसमें M square की value है. If 23 divides M square, then therefore 23 divides M. Result 3 by theorem 1.3. Theorem 1.3 क्या था? If A divides B square, then you can say A divides B. Why? 23 divides M square, then 23 divides M. अभी उल्टा. M is a multiple of 23. I.e. M is equal to 23 के. यहाँ 23 लग गया. So this is multiple of 23. Correct? Squaring both sides. Therefore, M square is equal to 529. 23 23s are K square. Alright. Now what is the value of M? 23 N square. So put value of N. 23 N square is equal to 529 K square. 23 ones are 23, 23s are. So what you got? Therefore, N square is equal to 23 K square. This is multiple of 23. So 23 divides N square exactly. Therefore, 23 divides N square. Therefore, 23 divides N. Result number 4. Again by using theorem 1.3 here. but no need to write every time. Now result 3 or 4 dekho, 23 divides m, 23 divides n. So 23 is a common factor of m and n both. So how can be the HCF of m and n be 1? They cannot be co-primes because the only common factor for them is 1. But here common factor is 23 for both m and n. So I can write here by, excuse me. Alright? By 3 and 4, it follows that HCF of m and n, जो हमने 1 कहा था, वो 1 नहीं है. By 3 and 4, HCF is not 1. If that is not 1, there is contradiction. This contradicts the hypothesis in 1. Therefore, our supposition that root 23 is rational is wrong. So what is right? Therefore, root 3 is irrational. Rational wrong है तो उसका मतलब irrational है. Irrational. Prove. I hope consolidation work is done as far as this question is concerned, and very important for the board exam as well. I'm going to give you plenty of homework. Alright? So study well. Watch this video again and again if you don't understand. But see that the concept is very clear to you.